Day 12, AP Physics, page 313, number 58. Here we have what's considered to be a simple pendulum. We have a single mass at the end of a string. We're assuming the mass is more or less a point particle. The center of mass is what we're looking at for that single mass. We're pulling it back from its lower position. And the key here is conservation of energy. If I draw a horizontal line straight across the center of mass of the bob, the pendulum bob, in essence I've increased the height of that pendulum by just a little bit. I'm going to label that H as best I can. H is going to be from this spot right here to the center of mass down here. So that's H. The pendulum string itself has length L from the pivot point at the top to the center of mass, so that's L. And let me go back to the original here. So the big distance is L. On the vertical string, I have big L for the length of the pendulum, H for the height that the bob obtains when you pull it back before you release it. I'm going to mark off one more thing, and that is this segment right here, which symbolically is L minus H. It's the big length, L minus H. Let me do a little better on that. L minus H. Alright, and then we have our angle, which I haven't labeled yet. You've been supplied that in the wording of the problem above. Alright, now we have to prove the symbolic equation and its conservation of energy. So we've established all the labels and notations. And what's going to happen here is in the high spot, the pendulum bob, center of gravity, center of mass, has a GPE. And that GPE will be transferred to kinetic energy. So there'll be a loss in GPE will be equal to the gain in kinetic energy. I like to write it like this. Delta GPE equals delta KE. Some people like to write delta GPE plus delta KE equals 0 because technically one's negative, one's positive. I'm just looking at the absolute value here. And we can establish the fact that at the bottom, or use a reference frame that the bottom spot, there's no GPE, it's 0 GPE. So the loss in GPE will just be the initial GPE at the given height, little h. And if we establish that the pendulum bob is not moving at the beginning, the initial kinetic energy is 0. So the final kinetic energy is the change. So essentially we just have to find the GPE at the top symbolically, and that's just going to be mg, technically delta h, but in this case we can just put h, equals 1/2 mv squared, delta mv squared, but once again v initial is 0. The masses cancel out, so it doesn't really matter what the mass of the bob is. And you can start to see things taking form. If I rearrange a little bit, I have v squared, and that's my maximum speed. In the symbolism in the stated question, they want you to have v max. Well, that is v max. I'm not going to keep writing that, but that's v max squared equals 2gh. Now that looks almost like our answer. It's in a similar form, but way too simplified. The problem is I have this little h I got to get rid of. Well, so how do we find h in terms of the other variables? Bottom line is, if you look at the triangle in the diagram, and I'm going to use my known equation for cosine. I know that the cosine of theta sub I equals the short leg, L minus H, or I should say the adjacent leg, L minus H, over the hypotenuse L. So if I rearrange that, I'll have L cosine theta sub I equals L minus H. And then if I rearrange things and get the H by itself, but a positive, I move the H to the left and then the L cosine theta sub I to the right, I end up with H equals L minus L cosine theta sub I. And essentially that's my last thing. I'm going to take that and plug it in for the H over there and then just factor out the L. I have my answer. In other words, take this and sub it in for H and factor out the L from that binomial.